This lesson we're going to look at partial variations. We're going to understand why a relationship is a partial variation relation. We're going to model a partial variation relationship with a table of values, a graph, or an equation. We're going to solve problems involving partial variation relationships, and we're going to compare direct and partial variation relationships. So the outcomes, much like in the last lesson, we're going to explain why the points should or should not be connected on the graph for context. Relate slope and rate of change to linear relations. Identify a linear relation as having a direct or partial variation relationship. Create a table of values for a given equation of a linear relation. Solve a contextual problem that involves the application of a formula for a linear relation. And write an equation for a given context, including direct or partial variation. So again, we're going to concentrate in this video on the partial variations. So what's the difference between a direct and a partial variation? In a partial variation, one variable in a linear relationship is a fixed multiple of the independent variable plus a constant amount. For example, the y value is always 3 times the x value plus 2 more. In a graph of a partial variation relationship, the constant amount is the y-intercept, and the fixed multiple is the slope of the line. So the slope of the line is the fixed multiple, and the y-intercept in this case is not going to be 0. In a direct variation, we said that a line will always pass through the point 0, 0. In a partial variation, that is not the case. So we're going to look at modeling a partial variation relationship with a table of values. Colton repairs heating and air conditioning systems. When he is out on a service call, he charges a service call fee of $75 plus $65 per hour for his labor. So just to get him out there is $75. So what are the initial value and the rate of change? Well, like I said, just to get him to the site for the job is going to cost you $75. So the initial value in this case is $75. The rate of change is the amount he charges per hour. So for every hour, the value or the amount charged is going to increase by $65 if that is a constant multiple. So every hour he's going to charge $65 more than the previous hour, plus at the end he's going to also put a $75 charge on top of that. So we're going to create a table of values for the cost of Colton services for 0 hours of work up to 5 hours of work. And we're going to see how the table shows the initial value and the rate of change. So we set up our table, and in hour 0, if he works for 0 hours, just for showing up at the job, he's still going to charge you $75. So the total cost is going to be $75. If he works 1 hour, he's going to charge you the $75, plus he's going to charge you an additional $65 for the hour of labor. That works out to $140 for 1 hour of work. And we add $65 every additional hour that he's working. So in a nice neat version of the table, these are the results we should get. For 0 hours worked, he's going to earn $75. Just for showing up at the job, he is going to be owed $75. If he works for 1 hour, he earns $140. If he works for 2 hours, he's going to earn $205, and so on and so forth. Every time the cost is going to increase by $65. So how does the table show the initial value? Well, the initial value is the cost for no hours worked. If he just shows up at the job and he hasn't worked a minute, he's still going to earn $75. The rate of change, we're going to see that After 1 hour of work, he's going to earn $65 extra. If he works for 2 hours, he's going to earn an additional $65 over what he earned for 1 hour. If he works for 3 hours, he earns $270, which is, again, $65 more than what he earned for working 2 hours. So we can see our rate of change happening there in our table. So when time is 0, the charge is $75. This is the initial value. And each hour, the total cost increases by $65. This shows the rate of change. So predict what a graph of the table of values would look like. The points on the graph will be linear because we have a constant rate of change. In other words, if you recall from our previous lesson, the constant rate of change is a slope. And the y-intercept, in this case, unlike in our last lesson, our y-intercept is not going to go through 0, 0. In this case, it's going to be 75. So our graph is going to look like this. We have a y-intercept of 75, and we have a slope, a constant rate of change, of $65 an hour, or 65. So what does Colton charge for a job that takes 1.5 hours? Show your work. Okay, for a partial variation, our equation is a little different than a direct variation. The equation would be y equals mx plus b, where m is the slope, or rate of change, and b is our initial value, otherwise known as the y-intercept. In this case, x, the number of hours worked, is 1.5 because it is our independent variable. M is our slope, which is 65 because he charges $65 an hour. And B is our initial value, or y-intercept, and that is the flat rate that or the flat charge that he adds to his price, which is $75. So we put those values into our equation for the variables m, x, and b, and we get y is equal to 65 times 1.5, $65 an hour times 1.5 hours worked, plus the $75 additional, and that'll give us a value of $172.50. So for 1.5 hours worked, Colton is going to charge $172.50. So explain why the cost of a 2-hour repair is not double the cost of a 1-hour repair. If you recall from our table, a 2-hour repair would be $205. In a partial variation, because the initial value is not 0 on one variable, that should say, is not a multiple of the other. The rate of change is a multiple of the hours worked in this case. He earns $65 additional every hour he works. But the initial value is always added on later, and only the one time. So he earns $65 for every hour he works, plus $75 extra on top of that. So we see that for 1 hour of work, he's going to earn $140, and if we double that, we should get $280, but we actually get $205. So this example, we're going to take a look at a partial variation relationship with a graph. Tanika borrowed $400 from her parents to help pay for a driver training course. She needs to have a driver's license to apply for a job that she wants after she graduates. She has an after-school job and agrees to pay her parents back at a rate of $50 at the end of each week. Tanika is keeping track of how much she owes her parents on a weekly basis. And you can see on the right there how much she owes every week. Before she starts paying anything back, she owes the full $400 to her parents. After 1 week, she's paid them $50, so she still owes $350. After 2 weeks, she paid them another $50, so now she only owes $300. After 3 weeks, she paid them again another $50. So now she owes only $250. What are the initial value and the rate of change of this table? The initial value is $400. It's how much she owes her parents at the beginning of her repaying the loan. And in this example, the amount owed will be reduced every week. So she starts off owing $400. After 1 week, it's only $350. So her rate of change is actually going to be a negative number in this case. It's going to be negative $50 a week. So the amount she owes is reduced by $50 every week is what we're seeing here. So we're going to create a scatter plot of the data. We're going to take the values in our table and create a scatter plot for them. And this is what we should see. We have a y-intercept of 400, and we have a slope, a rate of change of negative 50. And you see the note there. A negative slope means that the graph goes downward from left to right. The change in the rise is negative, while the run is positive. In other words, as our independent variable, the weeks, which is our horizontal axis, as that gets bigger, as that increases, the amount owing, which is our dependent variable, is going down in value. So as one increases, the other decreases. A negative slope occurs when we have a negative linear relationship, negative linear trend. Decide whether to draw a line, dashed or solid, through the points. Explain your decision. So in this case, should we draw a line through our data? The amount owing only goes down once a week. She only pays them $50 every week, so it happens once a week. It's not continuously dropping in value. So no line should be drawn through the data in this case. So basically what we're saying is, supposing she pays her parents every Friday. Every Friday, the amount she owes is going to be $50 less. But on Monday or Tuesday or Wednesday or Thursday, and of course Saturday, Sunday, she still will owe the same amount for all those days. Then on Friday, it'll go down again. How does your graph show the initial value and the rate of change? Well, in the graph, we saw that the y-intercept is at 400. This is what is owed before Tanika has returned any money to her parents. That is the initial amount of money that is owed. And the rate of change, we could see that every week the amount owing to her parents goes down or is reduced by $50. This shows a rate of change of negative $50 a week. And how do we know that the graph represents a partial variation relationship? Well, it is partial. It's a partial variation because it does look to be linear. It does have a straight line pattern, and it has a constant rate of change. The constant rate of change, or our slope, is negative 50, but it does not pass through the origin. It doesn't go through the point 0, 0. Our initial value for this particular graph is 0, 75. So our y-intercept was y equals 75. Suppose she paid back $80 every week. So instead of paying $50 back every week, she would pay back $80 every week. How would our graph compare to the one in part B? Well, if she's paying $80 a week, she's actually paying more back to her parents every week, an additional $30 every week. So the rate of change is bigger in size. It means the amount owing will be reduced quicker. And our graph would still be linear because it's going to be reduced by $80 every week. So our amount owing is going to reduce still at a constant rate, but it will appear to be a steeper graph. And here we can see our graph if she pays it back at $80 a week. In this case, it only takes her 5 weeks to pay back her parents, whereas if she was paying them back at $50 a week, it would have taken her 8 weeks to pay them back. And you can see that the slope calculated is going to be -80 in this case. So Cassie decides to lease a car for her new job. She makes a down payment of $1,700 and payments at the end of each month of $233 for 3 years. Write an equation to model the relationship between the total amount spent on the lease and time. So recall from our first example, we said that for a partial variation, the equation of the relationship is y equals mx plus b. The two key pieces of information here is the m value and the b value. M is our rate of change and b is our initial value. So m is our slope or rate of change. In this case, she's paying $233 a month. So that should actually be reading -233. Oh no, sorry, not in this case. We're looking at how much she's paid out. So she pays out positive $233 every month. The initial amount is her down payment. The initial amount in this case is a $1,700 down payment. So her M value is 233. Her initial amount is 1,700. So the equation would be y equals 233x plus 1,700. Of course, x represents the number of months that she's paid out, and y would represent the total amount that she's paid for her lease. Use the equation to determine what Cassie will have paid by the end of the first year and the total amount she will spend over the 3-year lease. And we're going to look at what we might notice from our two calculations. So after 1 year, how many payments will she have made? She will have made 12 payments because there are 12 months in a year. So the amount spent is going to be equal to $233 per month for the 12 months plus that $1,700 initial payment. So that will work out to $4,496. After 3 years, there will be 12 payments in a year for 3 years. That means there's 36 payments in total. So the amount she'll have spent after 3 years is $233 a month for 36 months, plus that $1,700 she initially paid out. And that works out to $10,088. And what do we notice here? That even though the time has been tripled, the amount paid out is not 3 times higher. 3 times 4,496 is going to be almost 15,000. Maybe around 13,500. But the amount that she paid out after 3 years is only $10,088. So, and why is that? Again, in a partial variation, the rate of change is going to be a multiple of the number of months paid out. But every time we're going to do it once in an equation, we add $1,700 to the value. So we're going to have 3 times as many payments. So 233 times 36 is 3 times as many payments as after 1 year. But then we tack on that $1,700 at the end. So predict and draw what a graph of the equation would look like. And again, what do you notice? What we should notice is that the graph will have points that appear linear. And the graph will have a y-intercept, because we said our initial value is 1,700. We're going to have a y-intercept of 1,700. The slope, the amount she pays out every month, is $233. So here's what our graph should look like. You can see that it is a linear graph, and that the initial value is 1,700. This does not pass through the origin. It appears to go very close to pass through where our two axes meet, but you'll notice that the first value on our scale of our axis is 1,500 in this case, and not 0, and that is for the vertical axis. So write an equation to model only the amount spent in monthly payments over 3 years. So we're not worried about that down payment now. We're only wondering how much money she has spent in her monthly payments. And how do we know that this relationship is no longer a partial variation? The new equation would be y equals 233x. So the amount of money she has paid out in total is going to be a multiple of however many months she has made payments. That is what a direct variation does. And it's no longer a partial variation because the initial amount of the monthly payment is not $0. After the first month, she's made a down payment, but she hasn't made any monthly payments. So the amount spent each month on the payments is a multiple of the number of months lapsed. In a direct variation, which is what we're looking at now, the amount of our independent variable is always going to be a constant multiple of the independent variable. So to summarize this, a partial variation shows a linear relationship between two variables, but it has an initial value that is not 0. In a direct variation, our initial value is 0. In a partial variation, our initial value is not 0. The rate of change is a constant, and it can be either positive or negative. And the rate of change will show us a multiple of our time, but we always tack on that initial value at the end of our calculation. The equation of a partial variation relationship can be written as y equals mx plus b, where m represents the slope or rate of change, and b represents the initial value or y-intercept. X is our independent variable because it's our horizontal variable if we were to graph it, and y is our dependent variable because that would be on the vertical part of our graph.